Okay, welcome to my second lecture on Lewis structures, and we talked about simple sharing of electrons, the simple covalent bonding concept for molecules that actually share these single reacting electrons to get to 8 electrons in their valence shell. Today I'm going to discuss charged molecules, this Lewis structure for charged species. So there are two classes of charged molecules. You could have charged molecules that doesn't have oxygen negative. You could have charged molecules that do contain actually oxygen negative. Today we're going to discuss about those that do not contain oxygen negative. So if they don't have any negative oxygens, what we're going to do, we're simply putting a charge for the central atom, working out the what would be the Lewis dot structure for the charged central atom, and then go back to the usual business of drawing the Lewis structure. So let's start without any delay about H3O plus. So what if I want to talk about H3O plus? I do O plus or O positive, and then oxygen is this. It contains 6 electrons. If I remove one of those to get a positive, because electrons are negatively charged, and if I remove one, it would give me a positive charge. So positively charged meaning moving toward less electrons, and negatively charged means moving towards more electrons. So if I have oxygen and it's going to be positive, I move one, because this is 1 plus charge, towards the left side. That's nitrogen configuration with 1 lone pair and 3 single reacting electrons. So that's the configuration. I have 3 hydrogens. I put the hydrogens here, each with 1 single reacting electrons. And if I just share these single reacting electrons, I would satisfy my hydrogens as I'm doing so. When I do the third covalent bonding, it would satisfy also my oxygen plus, because it would also have 8 electrons in its valence. So 2 here, 4, 6, 8. So 1 lone pair around my central atom and 3 surrounding atoms gave me a 4. And 4 is this framework of a tetrahedral framework. And a tetrahedral framework, if it does have 1 lone pair, which is the case for our molecule, it would give us a pyramidal geometry. Also, I have this model here. If I have tetrahedral framework and I have 1 lone pair, I need to just remove or detach one of these atoms to give me the correct shape. That is the pyramidal shape of this H3O plus molecule. We could also draw it real quick. I could just go on and do this. Now you don't have to do this, but you need to bear in your mind that this is going to be a pyramidal molecule. So you got to draw it in a pyramidal form. And for the H3O plus, now remember, the lone pair only sticks here. We don't put the lone pair here because the lone pair doesn't occupy shape. Okay, so that's when I actually detach. It means that the lone pair doesn't actually have any shape. That's why I detached this to give you the pyramidal framework. Actually, we will be left with the pyramidal framework, and the charge go outside the brackets for the whole molecule if you have a charged molecule that doesn't have O negative. This is O positive, by the way, so that's why we put the charge initially for the central atom, and we work out the geometry. After that, we put the charge for the whole molecule. That's the rule. Let's go to yet another example real quick. NH2 minus. Now NH2 minus, you have N negative, okay? And N negative means here, negative means moving towards more electrons. So just like oxygen, it has 6 electrons in its valence shell, okay? And if it has 6 electrons in its valence shell, it means you have to actually have the configuration of oxygen, 2 lone pairs, 2 single reacting electrons, 2 hydrogens. And when I share their single reacting electrons, it would not only satisfy the 2 hydrogens, it also satisfies my nitrogen negative. There are 2 lone pairs surrounding my central atom, and there are 2 surrounding atoms, gives me 4 again. Tetrahedral framework, but this time a tetrahedral framework that has 2 lone pairs. And here we go, with 2 lone pairs we get the bent geometry, okay, just like we had for water. So we have to remove in this geometry 2 of these elements, this one and this one, to get a bent geometry, as we could see. Also, we could go on and redraw the molecule real quick. Again, you don't, every time I do discuss a molecule, I do sketch this, how to say, this framework. You don't have to do this, okay? You could just bear in your mind what the correct shape is. Again, you could see that these lone pair doesn't go here, this lone pair doesn't go here, just to stick to the atom, and the charge should be negative for the whole molecule, and it's a bent structure. So this green framework, you don't have to have that. You just have to have the correct geometry, like in the bent form. So let's move on to NH4 plus. N plus, we could see that N is group 5, and plus means moving towards left, and that's carbon configuration. So this is going to be N plus. Remember, the symbol doesn't change. That's nitrogen plus, and it looks like the configuration of a carbon. And then 4 hydrogens, which is simply like this. So you have NH4 plus. Okay, now you have 0 lone pair, 4 surrounding atoms. Again, you go to the tetrahedral framework. Okay, so a tetrahedral framework with no lone pairs would just look like a tetrahedral, complete tetrahedral geometry. I could also redraw it in a better form. Again, you don't have to draw this green framework, but you have to draw the correct geometry. So anytime you draw a Lewis structure, there are 2 times. First, you figure out the connection, and then you figure out geometry based on the chart of the grand geometrical scheme. These frameworks that we're talking about, and the exit roads that gives you how many lone pairs. So what is your overall geometry? Here the geometry is a tetrahedral, and again the charge goes outside brackets for the whole molecule. Okay, so that's how I draw NH4 plus, and that would be the structure. Okay, now before moving on to some other examples, I want to go on very quickly on some of the structures. Now I want to also request any of you that is watching this video, whether you're a student or you're a professional, I want you to actually comment me and let me know if there's any molecule that I'm not drawing the structure for. Any of the chemistry books that I have here, if you go through all of them, there would be molecules in them. If you find a molecule that we're not discussing here, I would appreciate and I would thank you if you could just comment and tell me that you're not drawing this molecule in this series of videos of Lewis structure. I'll try to cover all of the possible molecules that you could think of. So CCl4, NF3, some of them would have same geometry as we have discussed before, so we'll just skip them real quick, okay? We don't go through them. All these molecules have carbon and 4 halogens. This one is the most common one. That is actually a solvent, carbon tetrachloride. So that's why I draw this. If you draw the same exact geometry to replace iodine for fullerene, or iodine or for fullerene instead of the chlorine, that would be the structure for that CCl4. Carbon, group 4. Chlorines, group 7. So they have 3 lone pairs each and 1 single reacting electrons. Okay. And that's this. So I have my carbon, I have 4 chlorines. I share this one, it would satisfy this chlorine. I share this one, it would satisfy this chlorine, this chlorine. And as I do this, the 4th chlorine, when I do the bond, it would also satisfy my carbon. 0 lone pairs, 0 at 4 surrounding atoms, 4. That's the tetrahedral framework. A tetrahedral framework again with 0 lone pairs would give you a tetrahedral geometry. CCl4 would also look like exactly like this. We want to redraw the Lewis structure because that is exactly the same as NH4 plus that we discussed. Also very exact same shape as the CH4, the methane that we discussed the very first session. NF3, nitrogen group 5, fullerene group 7, so 3 lone pairs and 1 single reacting electron. So you could share, as I do so, fullerene is satisfied, this fullerene is satisfied, and as I do this 3rd fullerene, nitrogen would also be satisfied. So Here 0 lone pair, my bad, 1 lone pair and 3 single reacting electrons. Again, tetrahedral framework, but this time a tetrahedral framework with 1 lone pair means that you will detach one of these atoms and give you a pyramidal shape. Okay, I won't draw the pyramidal. We've done this for H3O plus at the beginning of this session. We will do it for one more molecule here, and we have also done that for NH3 the previous session. Sometimes the students ask me, do we have to draw all the lone pairs for the surrounding atoms? The answer is no, it's not mandatory, but you have to draw the lone pairs for the central atom, and you have to understand that if you have fullerene, that is group 7, and at least for the first one you have to draw the lone pairs so that you understand how many bonds you need. Okay, this is how I draw a fullerene, and it has only one single reacting electron, so 1 bond. Okay, so that's for the first one, you have to draw it. For the others you don't have to, it's not mandatory. It's mandatory when you draw central atom. So this is OF2. When I do share this, I'll get fullerene to be satisfied. When I get the second covalent bond, it would not only satisfy fullerene but also satisfy my oxygen 2 lone pairs. These are the 2 lone pairs and 2 surrounding atoms. Again, for a tetrahedral geometry, this time you have a tetrahedral geometry. You have to detach this one and this one to give you a bent geometry. Okay, that's the bent geometry of OF2. This is just like water, like NH2 minus that we have discussed, so I'm not going to redraw the whole thing one more time. Let's go to 2 examples that have a stark differences. I'll draw them a little bit smaller here in order to actually make it obvious that charges and electrons are the final dictators for the shape. Let's compare CH3 minus to CH3 plus. Now C minus is carbon, and if you move towards this like nitrogen, it would look like this. So this is C minus. If I share the single reacting electrons, the first one would satisfy hydrogen, this one would also satisfy this hydrogen, and this one would satisfy my C negative. Okay, and the overall shape would be 1 lone pair, 3 surrounding atoms, a tetrahedral geometry with 1 lone pair would be pyramidal. So that's pyramidal. Let's just draw the shape. I just draw it carefully so that I could actually go on and put the framework after I draw the whole thing. Okay, and the charge should go to the whole mark. So that's CH3 minus, a pyramidal structure. Okay, what about CH3 plus? Now the CH3 plus, C plus, is just like boron. For carbon, moving to the left 4 or 3 electrons and then 3 hydrogens. C plus. You could see that my hydrogens are satisfied, my carbon is not. For beryllium and boron, I have actually circled them in blue. That's why these 2 elements or these 2 groups gave you compounds or these structures that are not very stable because it doesn't go to octet all the time. Okay, we will talk about how they could get more stabilized because they have a sort of weird bonding other than covalent bonding. Okay, so we'll talk this later on, but they would actually, the central atom, if it's from group 3 or group 2, they're not usually going to be satisfied through octet rule, but they're going to share their single reacting electrons. Okay, for this it's like this framework with 3 sides, or this molecule. This is the structure of CH3 plus. We could also view it like this. Okay, like from a side in a plane. Let's just look at the overall framework. When we talk about 5 or 6, it's kind of obvious that looking towards the plane, how useful it is. So it is useful to actually view it like from planar side, from the side. And I would just want to do this here just to compare the shape. So this is that plane. I have my C plus in the center. I have 1 hydrogen, 2 hydrogen, and 3 hydrogen. And if I just do this, it would actually be this, like this. Again, it's 0 lone pair, 3 surrounding atoms gives you 3. That's why you go to this framework. Okay, that's the geometry. You could look it from the side. That is instructionally useful, educationally useful, because when we go to 5 trigonal bipyramidal or 6 octahedral geometry, it would be very useful. So this is these two examples. So you could see just the change in the charge, CH3 plus, CH3 minus, they would have very different structure. CH3 plus being planar and CH3 minus being pyramidal. I would also want to discuss organic molecules, very simple organic molecules. You could actually draw loose structures of simple organic molecules, and we will do so as well here. C2H6, carbon, carbon, hydrogen, 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 hydrogen. Okay. My carbon is group 4, so it has 4 single reacting electrons. Each of my hydrogens has 1. I could share the single reacting electrons that will satisfy these 3 hydrogens, also satisfy this, and that would be 1 remaining electron on each carbon, and as I join them by 1 covalent bond, it would actually satisfy their hunger. If you have 2 central atoms, there is no shape or name for the molecule. However, you could decide, looking at each carbon here, there is 0 lone pair for both of the carbons, and 4 surrounding atoms, 1, 2, 3, 4 for this carbon here, and 1, 2, 3, 4 for this carbon here. So it's 2 of these tetrahedral structures connected together through one of those bondings. That's this one. So through one of the sides, you could see 2 tetrahedrals joined together. Let's go on to C2H2. That's my final example for this session. I'll wrap it up with that. Hydrogen, carbon. If I do connect one of the single reacting electrons, or the only single reacting electrons of hydrogens, I'll satisfy my hydrogen. The only way to satisfy my carbon, because it have 3 single reacting electrons, is to do a triple bond. Like I get the 3 single reacting electrons here being shared with the other 3 on the other carbon. And you could see there is 0 lone pair, 2 surrounding atoms. Like for this carbon, there's this hydrogen and this carbon. And also for this one, you have this carbon and this hydrogen. So 2 surrounding atoms for each of them. For both of them, the geometry would be linear. Okay? Because you have 2 surrounding, like the number 2, you would have the linear geometry. And that's this one. Okay, so for this carbon, that's the linear geometry. Also for this carbon, that's the linear geometry. So the whole molecule would also be linear. Let's wrap it up here for today.